The properties exhibited in the Josephson effect involve both quantum tunneling and Cooper pairs, so I'll teach you those first. Let's start with quantum tunneling. Suppose you drop a ball down a hill. Classically, when the ball rolls up the hill on the other side, it can't go any higher than the height at which you dropped it, even if there is a nice big slope on the other side, unless you give the ball enough energy to get over the barrier. But this is quantum mechanics, and in quantum mechanics, things work a little differently. The quantum world is probabilistic. Chances are, when you release the particle into a valley, next time you see it, it will still be somewhere in that valley. However, the particle would really like to be on the other side where the slope is. And there's a small chance that that's exactly where you'll find it. You could even find it in the middle of the mountain. So here's a junction. It's basically an insulator sandwiched between two conductive plates. An electron crosses the insulating barrier by tunneling to the other slice of the sandwich. Recall our mountain analogy. The middle of the mountain is the non-conductor, and quantum tunneling allows for the possibility of transport through the non-conductor to the other slice of the sandwich. For these non-superconductive electrons, an initial voltage must be applied before the current across the barrier is formed by quantum tunneling. When ordinary metal conducts electricity, the electrons carrying the current collide with imperfections in the metal, thereby creating resistance. But when a superconducting metal is cooled to its critical temperature, electrons pair off into Cooper pairs! Any movement of one electron is matched by equal and opposite movement of the other. As a result, they don't hit the imperfections. No electrical resistance is generated, and the electrons flow freely without the addition of more energy wasted. Here's a short explanation on how Cooper pairing works. A passing electron attracts the lattice, causing a slight ripple towards its path. Another electron passing in the opposite direction is attracted to that displacement. The flow of Cooper pairs is a supercurrent. It's a current that flows indefinitely without any voltage applied. Before Josephson's prediction, it was only known that normal, or non-superconducting, electrons can flow through an insulating barrier by means of quantum tunneling. Josephson was the first to predict the tunneling of superconducting Cooper pairs. If two superconductors are separated by a thin insulating layer, then quantum mechanical tunneling can occur for the Cooper pairs without breaking up the Cooper pairs. The wave functions of the Cooper pairs on each side of the junction penetrate into the insulating region and lock together in phase. Under these conditions, a supercurrent will flow through the junction in the absence of an initial applied voltage. And that, my friends, is the DC Josephson effect. In conclusion, a singlet, or non-superconductive electron, requires an initial voltage before it will form a current and cross the gap. However, Cooper-paired electrons do not require an initial voltage before they will form a current and cross the gap, due to their interlocking phases.